Okay, we are finally getting to applications in section 6.3. Okay, so for the first one, it says an airplane travels at a speed of 500 miles per hour with a bearing of 330 degrees at a fixed altitude with a negligible wind velocity. Note that a bearing of 330 degrees corresponds to a direction angle of 120 degrees. Okay, I really only care about the direction angle, so I'm going to keep in mind that the direction angle is 120 degrees. Okay, the airplane encounters a wind with a velocity of 70 miles per hour and the direction of north 50 degrees east. What are the resultant speed and true direction of the airplane? So there's an airplane, it's getting pushed by the wind. And I want to see after it gets pushed by the wind, what happens to its speed and what happens to the direction it's pointing in. Okay, and when it says direction, it always means direction angle. Okay, so let me first consider the airplane. Okay, let's see, I'm going to call him A. Okay, the airplane travels at a speed of 500 miles per hour. The 500 is going to be his magnitude. And it tells me the direction angle is 120 degrees. So I'm going to go ahead and write that in component form. Because in order to add or subtract vectors, I need to change them to component form. Okay, so this is my component form for the airplane. Okay, now the airplane encounters a wind. That's called the wind W. Okay, the velocity of the wind is 70 miles per hour. Okay, so I'm going to go with 70. Now it tells me the plane is north 50 degrees east. It does not tell me the direction angle of the airplane, so I need to think about that. And I might as well figure out the whole thing then. Okay, let me draw the airplane since I have to do this anyways. So 120 degrees is about maybe around here. His magnitude is 500. He's quite large actually. Okay, now the wind is north 50 degrees east. Okay, so from the north line, from this line, he's 50 degrees to the east. East is to the right, so about 50 degrees this way. Okay, is the wind. How big is the wind? The wind is only 70, so the wind is very short actually. Okay, so think of the wind as being right there. In order to do the problem, I actually need his direction angle. The direction angle comes from the positive x-axis, so I need this angle here. Okay, well if this is 50 up here, and this is 90, this must be 40, so 40 plus 50 will give me a 90 degrees. Okay, so the direction angle of the wind must be 40. Okay, so now I can finish his component form. Okay, what are the resultant speed and true direction of the airplane? So I want to see what happens when the wind encounters the airplane. So I'm going to do A plus W to see what happens when I add the wind to the airplane. Okay, now in your calculator, I would just do, for the x component, do this plus this. You might have to play with the parentheses a little bit in order to get it to work. When I put it in my calculator, I get negative 196.38. Okay, then in the y component, 500 sine 120 degrees plus 70 sine 40 degrees. I get about 478.01. And in component form, this is what would happen when I add the wind to the airplane. Okay, now what are they asking me for? Okay, they're asking me for the resultant speed. Okay, if I want the resultant speed, I actually want the magnitude of what happened after I added them. And then for the true direction, they want the theta. Okay, so let me go ahead and get the resultant speed first. Let's see, the magnitude of A plus W is going to be the x component squared plus the y component squared. Oops, I put a decimal in the wrong place. There, I squished it out. And then square rooted it. Okay, put that entire expression into your calculator. So I got the resultant is 516.78. That's the resultant magnitude. And the unit should match the magnitudes of the other vectors. So they're miles per hour. You might want to just think a little bit if that seems reasonable. It was going 500 miles per hour. The wind made it looks like the wind made it go a little bit faster. So the wind made it go 516 miles per hour, which seems okay to me. Okay, now for the true direction, I actually want the theta. So let's find theta. So the tangent of theta is the y component of the resultant vector over the x component. Okay, I'm going to do the inverse tangent of that fraction. Okay, let me see what I get, and then I'll consider if that looks correct or not. Okay, I got negative 67.67 degrees. Direction angle should be positive. So I already know it's off a little bit, but let me look at the quadrant real quick. My resultant vector is a plus w, so this has an x in the negative, y in the positive, which means this is actually quadrant 2. This is not quadrant 2, so let me add 180 degrees. Okay, I got 112.33 degrees. That is in quadrant 2 because it's between 90 degrees and 180 degrees. So now I know the magnitude of the resultant vector is 516.78 miles per hour. And then the direction of the vector is 112.33 degrees. Okay, we're going to do 2 more examples. This one, example 11 and 12, are going to use the component form, but it's going to use a little bit of a different idea regarding that. Okay, so in this case, it says 149.3 pounds Santa statue is suspended between 2 buildings by 2 cables, one on the left and one on the right. Because the building on the left is taller, the cable on the left forms an angle of 56 degrees with the horizontal. The cable on the right forms an angle of 23 degrees with the horizontal. The tension of the cable from the taller building is 140 pounds. Find the tension of the other cable. Okay, I'm going to sketch a picture because these angles are going to be weird. Okay, now I'm going to draw the building, but the building doesn't really matter. But it did say that it was taller on the left. Okay, so there's a cord here. There's a cord here, a cable here, and then there's Santa hanging. Maybe he's hanging from a string. I don't know what he does. He needs a hat or something, doesn't he? I don't know. Doesn't matter about Santa. It matters about what the force is. Okay, now let me go back to the problem. Okay, so the cable on the left forms a 56-degree angle with the horizontal. So 56 with the horizontal. So this is 56 degrees right here. Okay, the cable on the right forms an angle of 23 degrees with the horizontal. So from the horizontal, this is 23 degrees. Okay, the tension of the cable from the taller building is 140 pounds. So that's going to be the magnitude of this vector is 140 pounds. Find the tension of the other cable. So that's my unknown right there, the tension of the right cable. Okay, what else did they tell me? They also tell me that Santa weighs 149.3 pounds, or his statue does. Since he's just dangling there, his vector is actually going straight down. Okay, I'm going to write a vector for each of these 3 things in this picture, and then I'll figure out what to do with these vectors. Okay, let me start with, let's do the one on the left. So the left, you don't have to label it. Okay, the left guy is going to be 140. The direction angle I need to be careful of because that has to come from the positive x-axis. So if I go from here all the way to here, that's 180 minus 56. So that's going to be 124 degrees for the direction angle. Okay, and then the y component, it'll be 140 sine 124 degrees. Okay, let me consider the tension in the right side. Okay, I don't actually know the magnitude of the cable's tension, so I'm going to use T. So T, the 23 degrees is already with the positive x-axis, so at least I know the angle. Okay, now I'm going to consider the Santa statue who's dangling. Okay, now his magnitude is 149.3 pounds. What's his angle though? Okay, since he's actually going straight down, one way to call his angle would be this is 90, 180. This is actually 270 degrees. So I could write it out like this. Okay, and you could put that in your calculator and all that stuff. If you actually put this in your calculator, you're going to get that it is 0, negative 149.3 in component form, which kind of makes sense because if I think about the end of his vector here, the ordered pair for that would be the x would be 0 and the y would be negative 149.3. So you can either write it like this using the direction angle, or you could skip straight to this format if you recognize that that is what the result would be after you evaluate it. Okay, now the situation is, I know that Santa's not moving because otherwise he would be crashing to the ground or he'd be flying into space. Since he is not moving, this scenario has to add up to 0. Okay, now when I add up vectors, I actually add up their x's and their x's and their y's separately. So let me consider each scenario separately first. Okay, because he's not moving, I know that all the x components have to add up to 0 because the resultant is no one is moving. Okay, so if I just look in the x direction, if I do 140 cosine 124 degrees plus the x component of the right plus the x component of Santa, it should add up to 0 because no one is moving in this situation. Okay, now I could actually solve for the tension just using this one equation. So let me try that. Let me say t cosine 23 degrees equals negative 140 cosine 124 degrees. And if you make these decimals earlier, that's fine. It just depends on the calculator you're using. Okay, so I'm going to do negative 140 cosine 124 degrees. And I'm going to divide cosine 23 to the other side. So I get the tension in the rope is about 85.05. And what is the units? Pounds. Okay, and I'm actually done with the problem now because it asked me what's the tension of the cable on the right. Well, it's about 85.05 pounds. And I found that only using the x components. Okay, so I'm done. I don't have to do anything else. However, just to show you a different way I could have solved this, if I didn't want to use the x components, I could have just used the y components. Sometimes one looks easier than the other. If I had done the y components, I would have said 140 sine of 124 degrees plus t sine 23 degrees minus 149.3 should equal to 0. And I should be able to solve for t using this equation as well. I would never need to solve it both ways. But if you had the time and you wanted to double check your answer, that would be fine. And if you already decimaled everything, that would work as well. My answer will not be exactly the same because these are approximations. So I'm doing 149.3 minus 140 sine 124. I'm dividing the entire thing by sine 23 degrees. And I got about 85. I actually got 85.06 pounds. But that's pretty close. And that would be a reasonable answer. But again, you don't have to do it both ways. If one of them looks easier than the other, then look at it and see which one looks easier and do it that way. Okay, final example has the most algebra, but it's the same concept as example 11. It says two people are holding up the ends of two ropes with equal tension to hold up a suspended 200-pound crate. Each rope makes 65-degree angle with the horizontal. Find the tension in each rope. Okay, so there's two ropes, one on the left and one on the right. They each make 65 degrees with the horizontal. They have equal tension, so I'll go ahead and call them each T. And they're holding up a 200-pound crate. The crate is pulling down because gravity. Okay, find the tension in each rope. Okay, so let me consider each of these ropes. There's a left rope and there is a right rope. Here, let's call this, we'll call one of them rope 1 and one of them rope 2. Okay, let's make this rope 1, just so you know what I'm talking about. Okay, so for rope 1, if I write him in component form, he would just be t cosine 65 degrees, t sine 65 degrees. And I am trying to figure out what t is because that's the tension in the ropes. Now rope 2, that should be a 2, has the same tension, so that's not going to change. The direction angle is not the same though, because remember the direction angle has to come from the positive x-axis. So I actually need this angle in order to put it in component form. If that's 65, if I do 180 minus 65, the direction angle for rope 2 must be 115. So rope 2 is going to be t cosine 115 degrees, t sine 115 degrees. Okay, now for the crate that's pulling straight down, Okay, remember there's two ways to think about it. One would be, what is the direction angle of this guy? The direction angle of this guy is actually 270 degrees. And his magnitude's 200, so I could say 200 cosine 270 degrees, 200 sine 270 degrees, and it would be fine to work with it like that. If you look at it and you can tell it's pointing straight down in the y direction, you could also just write this as 0, comma, negative 200, which is what you get when you put 200 cosine 270 degrees and 200 sine 270 degrees into the calculator. Okay, now on the previous problem, we were able to solve by using only the x component or only the y component. So let's just set up the x component and see if we can solve it that way. Okay, so if I only look at the x components, because the crate is not moving, the sum of these vectors must add up to 0. Okay, so let's see. So in the x direction, this plus this plus 0 must equal to 0. Okay, let me try to solve this. I'm going to get t cosine 65 degrees equals negative t. Okay, let me put it in the calculator and see if I can do anything with that. Okay. Okay, I end up with this weird equation, 0.4226t equals 0.4226t. I could subtract them, but it's going to give me inconclusive answers, so the x components are actually worthless to me. They didn't lead to any conclusion that was useful, so I'm going to have to switch to the y components, and hopefully those will give me better results than the x components did. Okay, now if I go in the y direction, t sine 65 degrees plus t sine. Okay, let's see. I'm going to move the 200 to the other side. Okay, and then I think it's time to consult my calculator. So I'm going to do sine of 65 and sine of 115. And if you can add those up at the same time, you're welcome to do so. 0.63t equals 200. Let's combine the like terms. 126t equals 200, and then if I divide both sides, I get the tension in the rope is 110.3, and the units on this should be pounds to match the crate. Okay, so I got the same. I got 110.3 pounds. I had to use the y components only because the x components were inconclusive and didn't give me any useful results.